Now we did something kind of along these lines in the fourth module where we started showing, hey, there's ways that we could put this line into this cluster, this scatter, this cloud of points that are on my scatter diagram here. And there's a variety of different ways we could do it, but whichever way we end up drawing that line in there, this becomes a way of making predictions about the values of y based on the values of x. X becomes kind of a predictor of what's going to happen. It's going to become an independent variable, but we're not ready for that term just yet, that can predict the values of y. So any value we could come up with for x now, we could say, here's x3. Okay, x3 is on the x-axis there, and if I follow up, see that's the value of x that was corresponding to that point x3, y3. Okay, but x3 itself, if you continue it all the way up to the line that we just drew and then extended it over to the y-axis there, that would be an estimate of y. That would be y hat. In fact, because it's associated with the third observation of x, x3, it is y hat 3. So it is the estimate of y based on this best fit line that we've put in here. That is, it's associated with where on that line that we just drew, x3 on the x-axis corresponds to y hat 3 on the y-axis, just corresponding to the point along the line. It's not the same thing as y3. y3 is not exactly the same thing as y hat 3. Y hat 3 is our estimate. y3 is what really happened. So there will always be a distance between these estimates, like y hat 3 or y hat 5 or y hat 4, as I have on this slide here, and the real y hat y3, y5, y4, or whatever. In other words, there's a little distance. See how I drew them on there with the little dashed lines there? A little distance between these locations on the line and what really happened. What were the real coordinates of x, y, x, I, y, I? And that distance between, say, y4 and y hat 4, or y5, y hat 5, or whatever, is called a residual. Okay? The term is kind of similar to anomalies. The distance between a point and its average, the average for that sample is an anomaly. The distance between a point and its location on the best fit line is a residual. So this idea of the residuals helps us understand what a best fit line is. The best fit line is one that minimizes the sum of the squares of the residuals. So let me show you what that's going to end up meaning here. I mean, we could start with our little cluster of points here, our 9 points, that each of which corresponds to an ordered pair, xi, comma, yi. And we could ask ourselves, what would our best fit line for this look like? I mean, here I drew a line in just with a ruler, and I drew all my residuals on here, and I could measure them or calculate them and then square them and add them all up, and there would be a certain amount of a sum of squares of residuals. And these lines look a little long. It seems like if I pitched the best fit line a little bit differently, I might get shorter residuals. So I tried that here. This is worse, I think. Here I drew another line just with a ruler, and I sketched in what the residuals would look like and so on. And some of these residuals are not so big, but some of them are plenty big. Let's see if we can come up with another best fit line. Can we come up with a line that would be a better fit? Well, here I pitched one in here that I don't even like the sign of the slope of this line. I mean, clearly here, this line that I drew in, the residuals are huge. Clearly the sum of the squares of these residuals is going to be a very big number, so I don't like that one at all. In fact, with some experimentation, I think it turns out that this is probably my best fit line. It doesn't look too bad. I mean, obviously we're going to turn out that we can compute what the best fit line is, but it's going to be the one that has minimized those residuals. It's going to kind of pass through most of the points with as little error, as little residual as possible. So we drew a line here. And now I want you to think about how we draw lines in like an algebra class. I mean, a line is just mx plus b. Or to rearrange this a little bit, y equals b plus mx. Where b is the y-intercept of the line. That's the value of y when x is equal to 0. It's how far up the y-axis the line crosses. And m is the slope of the line. Well, for various reasons, we don't use when we're doing a correlation, a best fit line, we don't use the symbols B and M to describe the y-intercept and the slope of the line. Your textbook uses the symbols A and B, where A is the y-intercept of the regression line and B is the slope. So in this case, that regression line, that best fit line that was put in there, could be written as y hat of I is equal to A plus B times x hat. And that would be cool. And the equations for that A and that B are given in your textbook. They're on page 218. Now, I hope I'm not stirring up a big problem, but here's the deal. Never have I seen anyone use the symbols A and B for the y-intercept and slope of a regression line, or a best fit line, or whatever word you want to say. Regression is this process of trying to fit a line to the data. It's always either beta 0 and beta 1, no one says beta 0, beta naught or beta 1, where beta naught is the y-intercept and beta 1 is the slope, or it's B naught and B1, where B naught is the y-intercept and B1 is the slope. Why beta naught? Why betas and B's is the difference here? It's a difference again between parameters and statistics. The real phenomena X and Y are related to each other according to some best fit line that is described by beta naught equal, I'm sorry, the Y equals beta naught plus beta 1 times X. Based on the sample that you took, you can compute the statistics B naught plus B1 X. So as much as possible, we're going to use that notation because while your book is using A and B, this is the only place I've ever seen that. And any place you look for documentation, any place you do this in any other software package, any other textbook, it's going to be in betas and B's. Okay, so our y-intercept will be like a B naught, and our slope will be B1. Okay, just to review then, we've got this random variable x and we've got this random variable y. Originally, we took this random variable y, just computed y bar, and figured out, okay, for our values, each value we had some anomaly, some distance that we were away from the value of y bar, and variance was proportional to just the sum of the squares of those anomalies. Now we have this regression line, this best fit line, that goes through our cloud of data when we express it as a scatter diagram in terms of x and y. And every point y of I has some residual that is the distance from the regression line or the best fit line to that point. And we could think about the sum of the squares of those residuals. Almost certainly, the sum of the squares of the residuals will be smaller than the sum of the squares of the anomalies. Remember, the sum of the squares of the anomalies was related to the variance, was proportional to the variance. We now have a smaller sum of squares, in this case the sum of the squares of the residuals. In fact, the better the relationship is between x and y, the smaller those residuals will get. This is that whole business of variance explained. We have now explained a lot of the variance in among the y observations by the relationship between x and y. This is where that term came from way back, 2 modules ago or whatever. So the idea of this regression line, this best fit line, this line with a slope A and, with a y-intercept A and a slope B, or better yet, like a y-intercept of B naught and a slope of B1, sounds like something that we really want to be able to compute, and of course you will be in this project. Is that something that we can get Octave to compute for us? As it happens, yes we can. In fact, if anything, the problem is Octave provides too many different ways to compute these regression or correlation type parameters, which is actually kind of a frustrating point. There's actually a lot of different ways to do this, and finding the best way to do it or the best tool that's going to work for us over and over again proves to be somewhat frustrating. If I were going to just single out, though, a fairly generic command for making best fit lines, I would say that we're going to be using this command that's called polyfit. Now I'm going to kind of dissect here this polyfit command that we're working with here. Polyfit has 3 arguments. There's going to be 3 parameters here separated by commas, And two of them are pretty straightforward. One is x and the other is y, where both x and y are one-dimensional columns of data. There's going to be the same number of values, same number of rows in both x and in y. They don't have to be called, of course, x and y. In fact, they typically wouldn't be. They might be something like data, parentheses, colon for all rows, comma, 1, which would be like all rows, column 1. And then your second argument, where now I have y, it might be something like data, parentheses, colon, all rows, comma, 2. For now you mean all rows, column 2. That would be a very common way to use that x and that y, not necessarily literally being an x and a y. That one that's at the end, that third argument there, most of the time that you're using the polyfit command to do the creation of a best fit line, you're going to want that to be a 1 here. That 1 tells us that this is going to be a first order polynomial. That is going to, the shape of the line that you are fitting to this data is going to have the highest order of any of the exponents on the x terms is going to be 1 in this case. You'll see later that we're going to be able to do nonlinear forms of regression, ways of making best fit lines that aren't straight but rather parabolas and things like that by changing that number. But for now, for any time you're just making a linear fit to the data by creating a best fit line, that's going to be a 1. Excuse me, these pages are really staticky today. Now, what's going to be on the left-hand side of this? Okay, so polyfit is a function that's built into Octave. On the left-hand side, I just called it dummy. You can call it whatever you want. I don't really care. It's a little bit confusing because what actually comes back is an array of, for now, 2 values. Okay, in practice, when we change that value of 1 over there on the right-hand side, we're going to get different numbers of values in this dummy array here. Dummy is a computer science term. It means like this is just something I'm using right now. Okay, I'll do something with this and call it something else later. Okay, I don't mean a dummy as in, I don't know, like an insult from a 1940s cartoon or something like that. So the output of this polyfit function is going to go into a 2-dimensional array called dummy. You don't have to create it in advance. Octave will create it for you. Again, dummy may not be the right word if you want to call it rabbit or hold the mustard or something. It doesn't hurt anything. The first value inside of that dummy array will turn out to be the slope. It'll be B1. And the second value, dummy 2, or hold the mustard 2, or whatever you decide to call it, is going to be B1, the y-intercept. So with this polyfit command, you can very easily compute the parameters of, well, the statistics, strictly speaking, of the best fit line, so that you can move forward then and create whatever you need to do to make a statistical model, as we're going to be doing in the next lecture. Before we move on though to the next lecture, let's do a question real quick. Question 3. Here's an example of a best fit line type equation right here. I've got yi is equal to b naught plus b1 times xi plus epsilon x plus epsilon of I. In that equation, epsilon I is called the blank. Is that the residual, the anomaly, the correlation coefficient, or the standard deviation? Yeah, it's going to take some maybe reflection on your notes that you took during this lecture and so on. Make your choice from one of the 4 options below this video, and we'll get a little feedback before we move on to the next lecture.